This week on our program, you will discover how our bodies defend themselves against the millions of germs that attack us. We are also going to talk about vaccines and cyclosporin, the anti-rejection drug. There are microorganisms all around us, on your living room sofa, in the air, on the ground, in the water, on plants and animals. It's a real zoo. If we could see the viruses, bacteria, and parasites surrounding us, we'd immediately want to live in a glass bubble. Some microorganisms are dangerous, even fatal, and they have a favorite target, the human body, where they find everything they need to survive and reproduce. Fortunately, skin is an effective barrier. Sweat, saliva, and tears are natural pesticides. Nasal and throat secretions and acid in our stomachs are traps microorganisms cannot easily avert. But sometimes they do succeed in breaking through our first line of defense. But then the invaders have to deal with a counterattack waged by what is called the immune system. Ever since man's appearance on Earth, human beings have shared the environment with millions of other living organisms. In order to survive, man succeeded in finding his niche among his visible competitors, whether they were tigers or mammoths. He also developed a complex internal defense system to fight off legions of invisible, voracious invaders that were potentially lethal. When we talk of invaders, we mean viruses, bacteria, fungi, and parasites responsible for the flu and other diseases like malaria, measles, and tuberculosis. This defense system, far superior in terms of strategy than any modern-day army, is the immune system. In our bodies, millions of highly specialized cells are in charge of waging this ruthless biological war against microscopic invaders. Let's take the flu as an example. The infection begins when a virus invades a person's body. It can enter by way of the respiratory tract and go for a cell. The cell is unable to defend itself against the invader. The virus immediately penetrates the cell, takes control of it, and forces it to produce other viruses, exact replicas of itself. Very quickly, the cell is completely filled with many thousands of identical viruses. The cell then bursts, releasing a first battalion of viruses, which ready themselves to repeat the exact same maneuver against neighboring cells. If given free rein, the viruses would manage to kill enough cells to eventually provoke the death of the infected person. But within minutes, the immune system detects the invasion and counterattacks. The first cells to come to the infection site are phagocytes. They are like garbage men of sorts, which patrol the entire body to get rid of foreign matter, as well as normal cellular waste. As soon as a phagocyte comes into contact with a virus, it ingests it. This destroys the virus, but more importantly, it produces on the membrane of the phagocyte a signal, which serves to trigger the counterattack. This first encounter gives the signal for the race to begin, between the invading virus and the immune system. The virus tries to multiply before the counterattack begins. The phagocyte must, as quickly as possible, come into contact with another type of cell, the lymphocyte T cell. To increase its chances of success, the phagocyte leaves the tissue and goes to the lymph glands. Here, lymphocyte T cells circulate constantly. The phagocyte finally meets a lymphocyte T cell capable of recognizing the signal it is carrying. It then forces the lymphocyte T cell to multiply. Fever begins. The lymphocyte T cells emit a series of chemical signals which cause the phagocytes to multiply. The glands swell. The lymphocyte T cells continue to prepare for battle. They enlist lymphocyte B cells. Lymphocyte B cells are like minute arms factories. They produce massive quantities of proteins called antibodies, which spread throughout the body. The antibodies attach themselves to the viruses and emit a signal. The phagocytes recognize the signal, attack, and kill the viruses. Even if some battles are won, the war is far from over. The viruses continue to multiply, sheltered inside the cells. Now another type of lymphocyte T cell, a killer cell, enters the fray. Killer cells are the only ones capable of detecting cells infected by the virus. The killer cell approaches an infected cell and bombards it with lethal protein. Some of the viruses scatter, but the phagocytes lie in wait, ready to devour them. The killer cell then delivers the coup de grace by chemically forcing the sick cell to devour its own genetic matter, as well as that of the virus. The victory is assured. One last type of lymphocyte T cell, the suppressor cell, puts an end to the war and to the production of soldiers. Finally, the lymphocyte B and T cells engaged in the first stages of the counterattack carry out one last task. They produce cells that will store in their memories for several years the identity of the virus which carried out the attack. A healthy person's immune system may take as long as 3 weeks to eliminate a viral infection such as the flu. If the same virus were to attack a second time, it would be eliminated before our body would even feel it. The body is said to have become immune to that particular virus. As far back as the 11th century, Chinese doctors had discovered the principle of vaccination. During a measles epidemic, some Chinese doctors would treat healthy patients by blowing a mysterious powder into their nostrils. They obtained the powder by grounding scabs taken off the pustules of victims suffering from this dreadful disease. But it wasn't until 1880 that Louis Pasteur laid down the scientific basis for vaccination. Since then, vaccines have been developed against TB, diphtheria, cholera, diseases we will probably never catch. But there was a time when people would have loved to know the secrets of vaccination. As complex and efficient as it is, man's immune system can be beaten. Epidemics such as bubonic plague, measles, typhus, which devastated the large European cities during the Middle Ages, are proof of this. Mortality rates decreased when, through public hygiene measures such as sewage systems and waterworks, societies managed to reduce the quantities of bacteria and viruses that came into contact with man. Preventive hygiene was a first step. The second was vaccination. All vaccines, whether against flu or tuberculosis, work on the fact that the body remembers the infections that have already attacked it. As you've probably noticed, children seldom get the measles or mumps more than once. The first infection allows them to build up defenses. Later, memory cells are easily reactivated if an identical virus or bacteria attacks them again. Vaccines, in a sense, forewarn the immune system about infections it may be exposed to. They do this by forcing the immune system to react to a dead or weakened bacteria or virus. The infection caused by the vaccine is benign and hardly felt, except perhaps for a slight fever. But it alerts and stimulates the immune system, which from that moment on will have learned to recognize, fight, and quickly destroy a viral or bacterial agent that could cause a real infection. To vaccinate entire populations against polio, ordinary flu, or any other disease, vaccines have to be manufactured on an industrial scale. The first step in manufacturing a vaccine is to produce massive quantities of the virus. These can only be produced inside living cells. Most often, they are inoculated on cell cultures or on the brains of young mice. The flu virus, for instance, is grown on chicken embryos. For a few days, the virus multiplies, destroying nutrient cellular tissue. Next, the vaccine undergoes a process whereby it is purified, concentrated, and in some cases rendered inactive. The purity and effectiveness of the solution obtained is controlled by injecting it on new cellular tissue or in animals. In the end, the vaccine is administered by injection, scarification, or orally. In a few rare cases, vaccines may cause side effects, so scientists are constantly striving to develop new and more effective vaccines, which are also safer. Future vaccines will be products of genetic engineering. Dead or weakened viruses will no longer be used. These new types of vaccines will only transmit to the body the virus's protein covering, its identification card. The immune system would recognize the ID card, and that would suffice to trigger a defense reaction without the body running any risks of infection. Some viruses, like the AIDS virus, change appearance very rapidly. Until now, it has been impossible to identify a specific marker for this virus. Moreover, the virus attacks the immune system itself. It's the perfect aggressor. Still today, despite the efforts of an army of scientists, its stratagems remain indefensible. Today's scientists know a great deal more about the immune system than Chinese doctors did back in the 11th century. But their discoveries are still often the results of pure chance. In fact, it was by chance that a team of Swiss researchers discovered a fungus containing cyclosporin, a compound capable of selectively blocking the activity of the immune system. Cyclosporin acts in the opposite way from vaccine. Rather than alert the immune system, it paralyzes it partially, preventing a grafted organ from being rejected as a harmful foreign organism. Fully developed organisms are equipped with an extremely sophisticated defense system to repel any invasion of microbes. Millions of cells are programmed to identify and destroy foreign organisms. They make up our immune system. But sometimes our overly zealous bodyguards can be a nightmare for medicine. This is especially true in the case of organ transplants. Excluding identical twins, there is a 1 in 10 billion chance of finding two individuals with the same genetic heredity. When an organ transplant is performed, the medical team looks for the highest degree of compatibility between the cells of the donor and the recipient. In spite of these precautions, the transplanted organ remains a foreign body for the recipient's immune system. No sooner is a transplant completed than lymphocytes issue an order to destroy the invader. To counter the rejection of a new organ, efforts have to be made to prevent the immune system from going into action. The doctors who pioneered organ transplants had understood this well. They administered medication so as to paralyze the immune system. Meanwhile, the medication left the patient completely vulnerable to infection by anything in the environment. That problem remained unsolved until a new medication was discovered, again by chance: cyclosporin. Extracted from a fungus, this new drug revolutionized organ transplant technology. Cyclosporin prevents the cells which identify foreign organisms from acquiring any information. They can therefore no longer implement a defense strategy against the transplanted organ. The great advantage of cyclosporin is that it does not paralyze the immune system completely. All the antibodies already present in the bloodstream remain active. Past lessons still serve, and so the frontiers of the body continue to be patrolled. Cyclosporin has been in use since 1978. The survival rate among organ transplant patients now stands at about 80%. Organ transplants, no longer considered an experimental procedure, have become almost routine. However, the use of cyclosporin in transplantation surgery is not without problems. It is highly toxic and causes numerous side effects. In the long term, it can even cause serious damage to the kidneys and provoke the growth of tumors. We still don't know how long the human body can tolerate the drug. At present, annual costs for cyclosporin treatment are high, and it may well be that transplant recipients will have to stay on the drug as long as they live. Scientists are therefore studying other ways to prevent transplant rejection. A combination of several drugs might mean smaller doses, fewer harmful effects, and less cost. The ideal remedy would ensure organ acceptance even after the patient has been taken off the drugs. Some medical teams are experimenting with cyclosporin to treat diseases related to a disorder of the immune system. Sometimes cells whose job is to defend the body lack discernment and attack the very organs they are supposed to protect. This is the case, among others, of diabetics who need insulin injections. In diabetics, the lymphocytes attack the insulin-producing cells of the pancreas, actually destroying them. Insulin is the substance that helps to convert sugar into energy, which all cells need. When a diabetic's pancreas is dysfunctional, he has to inject himself with daily doses of varying strengths of insulin. This type of diabetes is the third cause of death in industrialized countries after cancer and heart disease. Cyclosporin is very promising when a disease is diagnosed early. It prevents the lymphocytes from organizing the destruction of the cells in the pancreas. Cyclosporin treatment is still at an experimental stage, and in some cases, patients have not taken insulin for 3 whole years. So far, there has been no indication of relapse. Unfortunately, cyclosporin's side effects limit its use. A malfunctioning immune system may also be the cause of certain types of arthritis, cancer, and multiple sclerosis. The challenge ahead lies in finding a balance between letting the immune system function and suppressing its action. Researchers have begun concocting mixtures that can either reinforce or weaken the human immune system. These new drugs must be tested with a great deal of caution. They could destroy the fragile balance of an immune system that each and every one of us has inherited over hundreds of thousands of years of evolution.